Remember in this life, in this class, you always asking question like this, okay? What do the data looks like? If I knew X, can I predict Y? When working with graph data, okay, in this class or in the beginning, you're just trying to look at what the graph looks like. Okay, so in other words, this is the question that you're asking about graph. Let me give you an example. Can you tell a difference between this graph and this graph? So it just like this is about where are the data. This is about what does the graph look like? What kind of configuration? Now watch this. So let's say this is a graph. It's fully connected. Okay, this is called fully connected. And this is another graph. Okay, so same number of nodes, same number of vertex. This one is fully connected. This is like a closely knit community. Everybody knows everyone. This one, well, maybe only two people know each other, and this guy doesn't know anyone, right? Isolated. Okay, for example, right? So this, just like here, you're not trying to predict anything, but you're trying to say, where are the data? In this case, where are is not the question. It's what kind of relationship do we get? We get a closely knit community, we get a sparse community, right? That sort of thing, okay? Or in that example we were talking about earlier, like an arrow, is it unidirectional? Like it's always pointing one way, or does it point back? Okay, if it point back, you can think of it as cycling. Does that make sense? The nutrient, right? The nutrient goes from this bird, this animal to this plant to this bug to this animal, and it doesn't come down. But if it goes to this mosquito gets eaten by a bird, but then bird also gets sucked by mosquito. Then the nutrient comes back down, right? There's a cycling in there. So this is another thing. So there's a difference between acyclicกับcyclic versus cyclic. There's dense versus sparse. Okay? Sparse. So when it comes to data analytics on graph data, what it means is that when you take the graph data, whether it's edgeless or matrix, you turn it into a graph. Visually, think of this. These are different kind of graph. You want to characterize the graph connectivities. Okay? So this is obviously different from that. This is different from cyclic is different from acyclic. So when we say analytics on graph data, okay, we will, like I said before the break, we will always work with the matrix representation. But the meaning of it, you should think in terms of the graph picture itself. Okay, but nobody does an analysis on the graph itself. You have to turn this into a matrix, use mathematics to do the analytics. Okay, does that make sense? But the picture, you can have like a small picture in your mind. What are we talking about? Okay, so with that in mind, graph analytics on graph data means, okay, this is how it works. You take data, and usually this is in some kind of Excel, right? Excel, CSV, say, okay. You create a graph, but you don't work on the graph itself. You work on its adjacency matrix. Okay, right? Now, if the original table looks like a matrix, then it can go back and forth. But conceptually, you have to think of it this way. The data is where you store the number. That number represents reality of relationship. You construct graph to represent the abstract relationship between entities. But now you want to analyze or do analytics on it. You can't do it on jumbles of lines. You have to turn this into a mathematical matrix. Then you do analysis on it. Okay. But now look at my hand. But the meaning, it's not about the matrix. You perform the analytics on the matrix. The calculation is done always on the matrix. But the insight is about the graph. Okay. So what kind of insight? Let me give you an example. Give you an example. Okay. Now, I'm just going to have three things. I'm going to have this. Okay. And then, okay. Is this a graph? This is a graph, right? Okay. My question to you is this graph symmetric? Well, you can tell that it is symmetric, right? And that's what you want. That's really what you want, the analysis you want. However, like I said, you can never do it on the line. You have to do it on the matrix. So let's do this. So what I would do is turn this into a matrix. The matrix is going to look like this. 1, 2, and 3. 1 to 2, 2 to 1, 2 to 3. Oops, sorry. Okay. 1 to 2, 2 to 1, and then 2 to 3, 2 to 3, and then 3 to 2. Okay. The question is this symmetric? I have to turn this into the matrix and ask, does it equal to its transpose? Okay. Now this is simple. This is stupid, easy stuff, right? This is very easy stuff. But this is exactly how all a lot of the analytics on graph is done. I want to know some property about the graph. To find out property about the graph, I can't figure out by looking at the lines. I have to turn it into an object called adjacency matrix. Then I do some mathematical operation on it to get the answer. So whether or not the relationship is symmetric, meaning if I love you, you love me. If I eat you, you eat me. That's symmetric. Okay. The way to check for it is to see whether or not A is equal to its transpose. You know the transpose, right? So in other words, if you have a 45-degree line here and you flip it, it looks the same. Okay. So this is simple, right? This is simple. Okay. Now, okay. Let's say I have some graph. Okay. And even worse, I don't even show you the picture. I can ask the following question. Is that graph, the relationship, is it weighted? Well, all you have to do is look at the graph and look at the number. If the number is 0 or 1, then it is yes, no. If it is something like, well, 1.345, then it is weighted, right? You just look at the matrix. You don't have to look at the graph. Now, in real world, a lot of time what they'll do is this. They do this and they give a number 7, 2.3 or something like that. In a more fancy visualization, instead of doing this, they just make the line thicker and thin. Have you seen that? Okay. I'll send you a picture. It's actually one of the things I'm working on, metabolic pathway. It's just a thin arrow from this metabolite to that metabolite. But what they do is they take a blood sample and they see the quantity of certain metabolite. And if this pair of metabolite occurs a lot, they make a thick arrow. What is a thick arrow? It is a weighted connection. Okay. Okay, so this is the same thing, right? So I put number 3 here and I put number 0.2 here. So that's thin, that's thick, and it's the same thing kind of thing. Okay. What else? What else? I can do cyclic. These are all the things. So the problem is to ask about graph, you ask about matrix. So let me show you how it's done. Okay. So for example, okay, go back to your book. There it is. If the graph is cyclic or acyclic, you can ask. Okay. Now, in Mathematica, because they know that you're really working with graph, you don't have to convert it into matrix and then ask question. But theoretically, that's how it's done. And I want to show you how it looks like. So so all these property, guys, you can read. Okay. Cyclic, acyclic. Well, let's go for the first one. Sorry. Connected, unconnected. So that's a good one, right? Connected means that everybody can be reached. Okay. Everybody can be reached within an arm's length. Now, let's say you represent the graph. Are you guys connected? No, because there's a break right there, right? Okay. Well, in matrix, what would happen is that there's a submatrix. There's like a block structure, okay? So you don't connect each other. So that's connectedness. That's one property. What else? Directedness, acyclic. Okay. Now this can all be done in Mathematica to check the property. The built-in function always has the letter Q at the end. So if you want to know if this graph, I'm just going to quickly do. So this graph here, okay, cyclic or not cyclic? Okay. The question is it acyclic? Acyclic means it doesn't cycle. Okay. So imagine that food web, that food thing that you saw earlier. Imagine that this thing, this one arrow here is taken away. Okay. So it doesn't cycle back. Okay. And I asked this question, is it acyclic? The answer would be true. It's acyclic. Nutrients only goes one way, never comes back. But unfortunately for this data set, I can't use as an example because there is reversal here. Now the reversal doesn't have to be direct. If this goes to here, and this one goes to here, and this one goes to here, it's cycle as well, right? So it's not the bird eats a mosquito, mosquito eats bird. It could be paper, scissors kind of thing, right? Paper beats scissors, paper beats hammer, hammer beats scissors, okay? So that's a cycle. Okay. So you can do this. Now, this is how, so like I said, you want to ask question about this. In order to ask question about this, the computation is always done on the matrix. And in Mathematica, sometimes if you want to have like a heat map so that you don't look at the value, but you look at color, you can do this. And this is especially good for heat map for weighted graph because it's not 0 and 1, but it's a continuous number. So you can have like a hot number like red, okay? And a low number like blue or something like that. So different shades. Okay. Right. So these are the example. These are the example that we show you that I picked. It turns out these guys here. Where am I? Okay. So for example, this is dolphin social network. There are actually 62 dolphins in this biological study. So marine biologists, they go around, they can memorize which dolphin it is. So they study 62 of them. So you can see that there's some kind of like cluster, right? This guy's a loner. This guy doesn't know anyone. He only swim with this one. This one is more friendly, swims with everybody. Okay. So dolphins are like social animals. Okay. And some is more extrovert. So you can actually have extrovert dolphin and introvert dolphin. Okay. But the point is, there's no isolated dolphin in this case. Fine. Eurovision vote, Les Miserables. So these are all the examples. So it doesn't really, matter. Okay. Directedness, again, you see, okay. Now, yep, dragonfly, ladybug. Now here, oh, I don't know why it didn't work before, but embedding method. Yeah, it does work. I don't know why it didn't work before. I think, oh, I have to plot the adjacency graph. Okay, I know what it is. When I plot the graph, I can choose the embedding. So I can choose this style. So this is an automatic style. It comes out under automatic. Now let's say I want to go to grid embedding. So there's grid embedding. Okay, so this is the same thing as before, right? The 12th animal, but now it's arranged into a rectangular square tile. It's spring embedding. This is kind of like there's a physical model underneath. Circular embedding. This is also useful as well. Okay, so these are, think of this as, first of all, visualization. Okay, so these are all the here graph layout. So all the layout. Okay, but that's visualization. Now, what you can do is, once you get the visualization, let's say you like it so much, you can get the actual coordinate of this using vertex coordinate, but that's not that interesting. Okay, so here's something more interesting, but I think we don't have that much time, but I download the Thailand Tambon, or sorry, Changwat. Changwat is a province. Okay, these are all the province. Okay, and what are the lines represent? You want to guess? The line represent whether or not there is a border. So Tak, for example, has a border with Mae Hong Son, with Lampang, with Sukhothai, and all that, right? So, and this is Prajwap Khiri Khan. Prajwap Khiri Khan is like at the bottom, so it only connects to the north, Phetchaburi, and to the south, Chumphon. Okay. Now, here's an interesting thing. If this were a geographical Thailand, okay, this is actually, you can see that it looks like the map of Thailand, okay. But what if I want to ask in an abstract sense, which province are close to which province by number of connectivities? Okay, in a way like that map between a bird and owls and Tawi and all that. Well, there's some algorithm that does that, and it turns out this is how they make that representation in the abstract space. What it's saying is that Thailand looks like this in terms of relationship, border relationship. There's a lot of Changwat provinces that are fully connected to each other. And then the southern, there's a little bit of a clump here. And it's kind of like an isolated, long, lonely road, which is true, right? Because you can't get to the southern of Thailand without passing Prajwap Khiri Khan. There's only one line, okay? One line. Now, obviously, this means nothing, right? This means kind of like fun-looking thing. Oh, there's a northern, there's a sort of like northeast and cluster and all that. But if you think of this as, instead of border, think of this as actual street. You can imagine that certain road can cut off the entire southern part, right? So for example, if somehow, it's a weird, I don't know what the analogy works, but let's say that you need a passport to go from one province to the other, okay? And you don't have Prajwap Khiri Khan passport. There's no way you can get from here to here. Whereas for other, see, Prajwap Khiri Khan is there. It's like a bottleneck. Whereas here, if you don't have a passport to here, you can go around. This kind of sensitivity to connectedness is a lot more important in real life than simple things like dense or not dense. Okay, dense or not dense, you just count on how many collection. But this is very important. Okay, and this, by the way, is not. I'm just make let's pretend instead of province, these are your logistic hub, right? Then you can bet that your supply chain is more robust to disruption here than it is here. Right? It's obvious, right? It's obvious. Okay. And okay, so this is the kind of analysis you can think of. The point I'm trying to say is that with, say, with probability distribution, you talk about the central tendency, the dispersion, the tail end, the quantile. Those are the standard stuff you can ask. With graph, there are so many intricate questions you can ask. You can ask about the graph as a whole. Is it evenly spread? You can ask about individual node, whether or not this node, this vertex is so important. An extreme case would be this. Okay. And yeah, let me, to save time, I'm just going to draw on here. Okay. Let's say you have this thing. Okay. And you have a whole bunch of points. Okay. You have a whole bunch of points. Maybe I should go there. Should make it thicker. Sorry. Thick. Okay. If you have a whole bunch of points. Okay. Okay. Let me ask you this. Okay. This is one. Okay. So this is one group of friends. Okay. And this is another group of friends. Okay. And these are the connectivity. Okay. I'm not making a good straight line. Sorry. Okay. I don't know. Okay. So this is one connectivity. Okay. And there it is. I don't know why it wasn't straight line. Okay. This one here, let's make it a straight line. Okay. Let me ask you. Okay. Which one is the most is more vulnerable? This network or that network? Well, actually, depends. This one, everybody is equally important in a way, right? This one, if I sever this node, okay, you still have 5 people who can talk to each other. That's not so bad. So I can eliminate this guy. So this guy is not that critical. However, if I eliminate this guy, what happened? The whole thing breaks apart. Okay. So you can imagine, and the opposite case is, let's say the connection is like this. Look at the blue connection, guys. Okay. Now, the blue connection, everybody is important. You cut one person, it becomes a chain, right? It becomes a chain. So nobody is more important than the other. But with the red connection, this guy is more important than the other. Okay. Now, those you can eyeball, you can tell, right? But what if your network looks like that picture that I show you? That's like this. Okay. Now, in this picture, I can probably tell you that this guy can die and it doesn't affect everybody. Okay. But what about between this guy and that guy? Who's more important? Can you tell? This is also densely connected with everybody, right? Who's more important? Okay. So in an extreme case where you have a star formation, the guy's at the hub. That's why, you want to be the hub because you're the most important person. If you're in a ring, this is, by the way, it's called topology, this kind of arrangement. If it's a ring, everybody's equally important. If it's a star, nobody is important except one guy, right? So the idea is, what if in real life, it doesn't have that extreme case? It's something like this. How can you tell, is this guy and that guy, who's more important to that, to holding this kind of network relationship? Yeah, this guy, you can say that this guy can die and nobody care. This guy can die and nobody care. But what about this guy? Oh, you know what I mean, right? Something like that. Actually, you can't even tell if this guy is that can die because you don't know, you can't see. So what can you do? What you do is you apply analytics on the adjacency matrix. And that analytics, the most important one, come under what is called centrality analysis. Okay. So imagine this picture. Okay. I'm going to give a centrality score. Okay. Centrality score is like who is important in this network, like influencer. For the blue network, you know what I'm going to do? Blue network, I should give everybody equal importance. So everybody gets 0.2. Does that make sense? Right? Makes sense, right? Yeah, look at the blue first. Don't look at the blue. The blue network, everybody gets 0.2, 0.2, 0.2, 0.2, 0.2 adds up to 1. How about red? Oh, sorry, not 0.2. Everything divided by 6. Okay? Yeah, I should have, never mind. So the blue network doesn't have the guy in the middle. So 0.2, 0.2, 0.2, 0.2, 0.2. Now the red network has the guy in the middle, doesn't have the blue connection. What do you think is the score going to be? The score is going to be something like 0.9, 0.02, 0.02, 0.02, 0.02, 0.02. Does that make sense? Right? The question is, how do you make that centrality analysis? Okay, this fall under the subject of, dun, dun, dun. This is where you come in. Centrality analysis. Oops. Where's centrality analysis? There it is, centrality analysis. Okay. So centrality analysis, according to this centrality, let me tell you that there are 3 methods. Okay, there are 3 methods. I'm not going to tell you what they mean yet. Okay, there are the 3 different scoring scheme, let's say. Okay, according to this scoring scheme called PageRank, the most important animal is Tawi. The least important is sunflower. Why is that? Because this picture, the way they look at it, they look at connectivity. They don't care about where it came from. So this is not realistic because biologists care about who came from, right? So from a biologist point of view, maybe all the nutrients come from sunflower. So that sunflower is the most important. But if you just look at the picture, you will see that, you know, this guy, if you take this graph of this guy away, the graph still stands. So in that sense, this guy is at the kind of like remote. You can eliminate. Okay. So from that definition, the guy who is more connected is Tauhi. That's the bird. Okay. So how many ways of judging the centrality? Now look at Thailand. My question to you is this. Who is the most important province in Thailand? Well, that depends on the criteria, right? If the criteria is you are in the thick of things, chances are it's one of these guys in the middle. Okay? If the question of centrality or importance is without you, the country divides in 2. Then none of these people matter, none of these Jangwat matter, none of these province matter, because without this Jangwat, the other Jangwat can still get together. So in that case, who's the most important? This guy, Pajok Kiri Khan. Because if this guy doesn't talk to anyone, the North and the South are separate, right? So the meaning of centrality is dependent on context. Okay, now let me give you 3 definitions of centrality. Okay, one, it's very simple. The more you know, the more connection you have, the more important you are. This is called degree centrality. It's basically counting how many connections you've got. Okay, so if you know more people, you collect more name cards, you're more important. All right, so that's very easy. That's called degree centrality. Now, let's go back to Thailand. Yeah. How about I ask this question, and this is a very tricky question. Okay. If I ask question, which province is most important in terms of how many border it has with different province, Tak is the most important because Tak has more border with more province than anybody else. Okay. Now I'm going to ask something else. I'm going to say, okay, let's say that in Thailand there are, okay, rough, we say 70 jangwat, 7 province. Every person from every province want to go to other province. Okay, so create all the paths from Surat Thani to Mae Hong Son, Surat Thani to Nan, Surat Thani. Okay, and I want to say calculate the shortest path. So in this case, let's say shortest path is minimum number of province you have to cross. Okay, so if you have to cross 2 border, that's better than crossing 3 border. Okay, you can use this or you can use physical road distance, but in this case, let's use number of province. Okay, so the shortest path. Okay, so how many jangwat do we have? 70, right? How many travel? Let's say it's the bidirectional, so it is 70 times 69 different pairing. Okay, each pairing you would have to determine the shortest path. Okay, and I say the most important province is the one who appears in most shortest path. Does that make sense? Okay, so let's say you want to whisper to that guy. You have to whisper past him, past him, past him, past him, right? That's the shortest path, 1, 2, 3, 4. Okay, if you want to whisper to that guy is 1, 2, 3, 4. Now, notice because you are over here, right? And you are not connected to that guy in the back here. Whatever path you take, you're going to pass this guy. Okay? Now, in a way, if you want to pass this way, you don't have to go to that guy in the back. So, of all the 10 by 9, 90 conversation. Okay? 90 conversation, whispering from here to there, from here to there, from here to there, from here. Say all this. Just go by the shortest path, minimum number of people, because it's a secret. You don't want to whisper across many people. And I list all these 90 paths. How many times do you appear? How many times do you appear? How many times do you appear? Right? Chances are you're not as important because you only appear in 9 conversations. Because it's only conversation that involves you directly that passes through you. Whereas this guy is more important because not only do you have 9 paths from you, you also take her path. So wherever she goes, you definitely get another 9 right there, right? So if I list all the shortest paths and I count, who appears the most, think of this as a telecommunication junction. If you are always between conversation, you are important. This, therefore, is called betweenness centrality. Yeah, between centrality. Okay, so understand the concept. Okay, however it's calculated, Mathematica has a built-in function called betweenness centrality. Okay, it automatically gives you the score. Okay, What else? Okay, let's talk popularity. Let's talk popularity. Okay, now you are up. Give me 5 minutes. You're more popular if you know a lot of people. How would I measure that centrality? Degree centrality, right? Degree is the number of connections you have. However, what if you know 5 people at the rim? You also know 5 people in the middle of everything. Okay. In other words, you just know 5 people who doesn't know anybody else. But you know 5 people, each of whom knows 10 people. Right? So it's not how many people you know, it is who you know, right? So there's two concepts here. How many people you know is counting degree of the number of connections. That's called degree centrality. If you say it's not how many people you know, it's if you know important people. How do you say you know important people? If that person knows a lot of people. How do you know that person is important? Because he knows a lot of people. So it's a recursive question, a recursive definition. You know a lot of people who in turn know a lot of people, who in turn knows a lot of people, who in turn know a lot of people, who in turn know a lot of people. This recursive equation in matrix form is called eigenvector equation, okay? Eigensystem. And based on that, the one that has the highest importance from this criteria is called eigenvector centrality. Now, why does this matter? When I was halfway through my PhD, we started to have internet. I'm quite old. We had Netscape. I used Alta Vista as a search engine. Then Google came along. You know why Google came and beat everyone? Google came later. The reason Google came beat everyone is because by listing the website according to eigenvector centrality. Now, there's a modification. So it's called page rank. Okay? Because one of the guys' names Page, and internet has a page, so they call it page rank. But it's basically a version of eigenvector centrality. The same algorithm that I was using for the bank in Thailand. This website is important because it is linked to by a lot of websites who are in turn important because they are linked to by a lot of websites who are in turn important because they are linked to by a lot of websites who are important because in turn they are linked to by a lot of websites. See? Now, imagine, yeah, this says nothing about the page. So go to the beginning. In fact, I might as well finish the lecture with this sentence. In the beginning of the lecture, who you are, you have attributes. That would be like looking at the page. And is this page long? Does this page have English language? Does this page have a commercial transaction? This will be looking at attribute of the page. In this case, the page, I don't even care. It's just a URL. The importance is this page is linked to by a lot of pages that in turn are linked to by a lot of pages that are in turn linked to by a lot of pages. And by doing that, Google creates a rank that corresponds to frequency of travel or some kind of connectedness. So that's why when people start doing a search, Alta Vista did a search, Netscape did a search, everybody did a search, but they just rank it in a way that doesn't seem to help. Because the link that you go to, maybe you're searching for something like cough medicine, okay? So maybe one website say cough medicine 5,000 times. So you list that on top. But that website, nobody cares, right? Whereas the other website only mentioned cough medicine 3 times. But that website happens to be a very popular site that everybody links to. And that the website that links to that is also linked by a lot of websites. So it makes sense. People prefer that. And within a few months, maybe a year, maybe 2 years, let's say 2 years, Google just killed everyone. Okay. So the reason we have Google today, the monster that we have as Google today, is because they choose the right algorithm. Okay. So don't tell me that mathematics doesn't make money. Okay. Literally, this what the only thing, not graphical interface, not feature, nothing. It's just that Google can rank pages better. And they rank pages better because they have a graph representation of URL. Okay. So your homework, and then you can go. Your homework is to follow the book on the 3 centrality definition: betweenness, eigenvector, and I think page rank or between. Okay, pick 3. Okay, there are a few. There's also cat centrality, but never mind. So use page rank, betweenness, and degree. Let's say. Okay. Eigenvector, never mind, because page rank is also like an improved version of eigenvector already. Okay, so page rank, betweenness, right, and degree centrality. Okay, rank that for 2 example network. Okay, don't pick a big one, guys. Or you can pick a big one. Okay, the idea is that you will find out which one is more important, but remember, you have to look up the vertex label name as well. Otherwise, it's just going to be 1, 2, 3, 4, 5. Okay. Now, you can go, but I'm going to give you something to watch. Okay. So, how does this centrality work? Okay. Okay. Now, this is okay, so this is well, this is kind of social network visualizer. Actually, I'm gonna save time. I'm gonna go to a set of slides that I use. Let's call it PyCon. Okay, good. PyCon Thailand. There it is. Graph computation. Okay. I want to have one that, okay. Right. So this is I was giving a talk to okay. Let me see if I can find the one that's PDF power graph. Okay. Well, you guys can see this. It's a bit small. It's I can get rid of this. Yeah. Okay. Right. Okay. This is actually there's a city. There's a Russian enclave in the Baltic Sea. It used to be called Königsberg. Okay. This is what the city looks like. Okay. It has 7 bridges. 1, 2, 3, 4, 5, 6, 7. Okay. And there was like a 300-year-old question about, can you actually cross all the bridges one time? Okay. So you can't double up. Okay. Cross all 7, but once. Well, it turns out that the way to solve it with Euler is he doesn't look at the bridge like this. He actually looks at the destination as a vertex. He looks at the bridge as an edge. And then he creates a graph representation. Once created the graph representation, he did some computation. Now, in this case, he didn't have to translate into a matrix because it's very small and he can perform computation. And the solution is no, you can't. Okay, the solution is no, you can't. So this is 300 years old. Okay? This is very famous. But the concept here is, and you can't see very much. I used this concept when I was working for the Bank of Thailand to see which banks are important. So in the old days, we would say Siam Commercial Bank is important because market size, market share, or capital size or balance sheet. What I did was I looked at interbank relationship, who borrows from whom, right? Now, when I say important, I don't mean nice. I just mean important in the sense of the system is critically dependent on this guy not dying. So what I did was I looked at this bank, borrow from this bank. Does it borrow a lot? Does it borrow from a lot of bank? Does it borrow from a lot of bank that in turns borrow from a lot of bank? So what is it? Eigenvector centrality analysis of interbank borrowing. The idea is that you can be a small bank, but if you borrow a lot from a bank that borrows a lot, from a lot of bank who borrows a lot, from a lot of banks who borrow a lot, if something happens to you, the system breaks down. This was the first time that, you know, I kind of proposed this to the Bank of Thailand. And now, by the way, it's if you read like Basel document, it's a very well entrenched concept. It's not how big you are. Okay, before this, the concept was too big to fail. The bank that is big, the central bank has to hold, make sure it doesn't fall. Now we have, you can search that the change from too big to fail to systemically interconnected or systemically important to fail. And the best way to measure whether or not this bank is systemically important or not is whether or not it has a very high eigenvector centrality score in the graph representing the interbank borrowing network. Oh, that's a mouthful, right? So first of all, because I was working for the Bank of Thailand, I had data of banks borrowing from banks. This is not public data. So by the way, this is not published. So I could tell which bank, not I, but you know, there's a database that say which bank borrows from which bank. So which bank borrows from which bank? So it is directed, right? And it's not symmetric, and it is weighted, right? And I calculated the systemic importance. It turns out, and you can read this, the result was that, okay, let's search. Yeah, maybe I should have you read on this. And systemic importance. Okay, so this paper, okay, oops. I just want to show you one picture from the paper. Actually, I don't want you to read the whole paper. Ah, there it is. Interbank connectivity matrix. Okay, so let's look at this guy. This is extremely important picture because I'll show you why. Okay, so this is actually back when there were a lot of banks before consolidation. This is a kind of like connectivity, right? There it is. Okay, the blue line, I think. Yeah, sorry. The green line is volume. So if you look at this was a secret data bank, database. So I did not name the bank. I just used an alias. Okay. So if you look at the screen and say, assign some kind of colors to it, not the corporate colors. Okay. Here, you will see that this bank here is very important because the volume is high. It turns out that it's one of the smaller volume or medium volume that has a lot of network leverage. So another word to use is network leverage. It's the sixth bank from the left. You can see that it clearly is the most important bank. So if there's something happening in terms of liquidity, the Bank of Thailand should look after that guy, not the biggest one. Okay. In fact, it turns out not to be the biggest bank by any measure. But because of this network effect, this guy turned out to be the most important. Okay. So analogy would be, this is not a big web page, but if you were to do Google search, the sixth page would come up on top. Okay. Like pay attention to this guy. Look at me, look at me. This is so important. And you can only analyze that if you apply analytics on graph data. Okay. And that analytics is called eigenvector centrality. Okay. So do your use PageRank. Maybe it's more popular and it's in an improved version. So your homework, again, pick out 2 example network that you play with. Okay. Do a plotting, right? And if you can show the label as well, that'd be nice. You can do graph plot. You could do graph plot 3D, right? You can get extra point for doing graph layout. Okay. So if you look at the example, I want you to look at this guy. Okay. Not this guy. Yeah, this example here, this is where you work about different kind of centrality. So follow this section here, graph theoretic, centrality analysis, method, right? And demonstration. So so follow this example closely, but don't use the same data set, obviously, right? Finally, and this is an interesting thing. And this is from the presentation that I did. Where's okay, right. So this is also very interesting. This is connectivity. And I did the same thing. Okay, eigenvector centrality could be applied. Well, first to British Premier League, right? Who's more important? Who gets a lot of points by beating guys who beat a lot of guys? The team that's good is not just the one that gets the most points, but the one that beats a lot of team, that beats a lot of team, that beats a lot of team, that beats a lot of team. So what I did was and at that time, I think 5-10 years ago, Overwatch was a popular game, right? So what I did was I did a relative strength index for which character is more important or which character beats which character. So these are the score of which character beats which character. And I did an eigenvector centrality. It turns out that I think Zendaya, I think was I don't know, do you play, you know this game? I don't know. I just download this from the internet. Anyway, it's a character game. And so I did that. And now here's more interesting thing. It was this, right? Connectivity, okay? Connectivity. In Hollywood, there's this fun game called Kevin Bacon number. I don't know if you're familiar with that. Kevin Bacon is just an actor, okay? Kevin Bacon number is 1 if you appear in the same movie as Kevin Bacon, okay? If you don't appear in the same movie as Kevin Bacon, but you appear in the same movie as someone who appears in the same movie as Kevin Bacon, you get a Kevin Bacon number of 2. So that's basically connectivity, right? So here's Kevin Bacon. You appear in the same movie, 1. You don't appear in the same movie as Kevin Bacon, but you say appear in the same movie as him, who then appears in the same movie. Okay. The claim is that of all the Hollywood actors, nobody has a bigger number than 6. That means that you can always relate all the actors together through this kind of like sharing screen time. So an example would be randomly, you know, this is Kevin Bacon, right? Oops. I don't know why there's a black thing here, but okay. Kevin Bacon is underneath there. And he's in this movie with this guy who's in this movie with Bruce Lee. So Bruce Lee actually has a Kevin Bacon number of 2. Okay. Now, the idea is that this guy has a Kevin Bacon number of 1 because this is the monster in that movie. Okay. So this is what is called bipartite graph. It's a graph connecting movies to actor, right? So if movie to actor, I appear in this movie and this movie appears with that actor, then I share the movie screen, okay? Created that matrix to see that who is the most popular actor to appear with. Not popular for you, but popular amongst the, among the co-cast, okay? So this is actually the real network. I download this just for fun. By the way, this is what it looks like. This is with all the how many actors, I think? Yeah, there are actually, this many nodes and edges or arcs, okay? And based on this connectivity, so this is actually, I put the movie on the left, I put the actors on the right, and if you can go one way, that's 1. If I need to do twice, then it's 2. So I did this and came up with eigenvector centrality of actors in Hollywood. In other words, the actor that is so important because he acts in a lot of movies with a lot of actors with a lot of movies. And I was expecting this. I was expecting this kind of smooth. It turns out it's not. There is one person, there's one actor that is the most important. He's like the linchpin. Okay? He's like the key in all casting. Yeah, stand out for everybody. I can give you a hint. It's a guy. Okay, it's a guy. So there's some famous number here, but I don't know if you want to guess who it is. Okay. So all this can be done in a graph analysis. Let me give you another example. This is a travel graph. This is similar to what I was talking earlier, but instead of going from province to province, I was talking about different district within Bangkok. Okay, it's in Bangkok. So obviously, in this case, you can see that bordering is a symmetric relationship because the matrix is completely symmetric, right? You can take a transpose the same because if this and that share border, then there's no direction. Okay, and I think this one here, the most important is, I think Dusit, I'm pretty sure. I think it is Dusit. Dusit is like the district that sort of like, question. Chatuchak. Yeah, I think Chatuchak. Sorry, not Dusit. I think it's Chatuchak. Chatuchak is like the most key central node of Bangkok. Okay. So this kind of thing can be done with all things. So you can imagine that this is exactly what Google did, 30 years ago. Instead of ranking the listing of the Google search by the number of times the word appear, it would say, okay, you search cough medicine, you search travel to Bali or whatever, okay? And 100 web page comes up. Among the 100 pages, who points to whom? And the one who gets pointed to a lot by website, who gets pointed to a lot by website, who gets pointed to a lot recursively, would have the highest ranking. Google would then list 1, 2, 3, 4, 5, and then goes to the next page. based on that, people prefer the Google ranking to all other search engine. And that's how Google became dominant very quickly. In 2 years. It just kind of like kills everyone. Okay. Basically, success was through mathematics. Okay. So data analytics is that important. Now, next week might have some time to talk about graph computation in a more general sense, but what I want you to do then next week is more like your project now. Okay, I want to focus. So basically like last time, but I don't want you to just talk about it. Literally show as if you, let's think of it as, you know, you're trying to show as much as you've got. Okay. And you've only got one chance that you get feedback from me until you finalize. Now, what I would like to do, and tell your friend who's not here, is in tradition of Basai, right? Not only do you have a project, you have a presentation deck, which is a PowerPoint if you like, okay? However, even though, okay, that's not the essence. The essence is your computation program, right? But show PowerPoint, a little bit of motivation, this and that, and then do a video clip, post on YouTube. I'll tell you the instruction later, okay? But basically, you should be graded on the presentation in both the literal presentation deck as well as sort of like a project talking through with your like a video clip. Okay, I'm gonna have you name the name of the class or something so I can find it later. Okay, and then you can also turn in the code, right? So now I encourage. Now this is not critical. If your project not only has a data that you are working on, but if you can sort of like summarize something in a visualized form and put it on a demonstration page, that would be very cool. Okay, but don't worry about it if it's too much trouble. Okay, because demonstration only accept project that doesn't rely on external data. So since we're working on data, maybe it's not relevant. But if you can, that'd be nice. Okay, but otherwise show that. So again, it's going to be a lot of interactivity, and it's going to be about real data. Okay, how many of you are already okay with your data source? In other words, you know what data set you're going to work with. You should be like, by now you shouldn't have a hesitation. Okay, so you can embellish it, but you should have a basic data set that you're working on. Work on that, right? So again, think along the line of the book chapter. Okay, how much of it is your project can be 50% chapter 3, 30% chapter 4, or something like that, right? So 50% chapter 3 means it's all about interactive visualization. Okay, 30% chapter 4 is because certain things is about distribution of data. For example, you have one of your colleagues was working on earthquake data, right? So earthquake data is an extreme event, but if you just focus on the earthquake themselves, then among the data set, it's not a rare event, right? Because you're just measuring all the earthquake, and then you can fit the distribution of the strength. Okay, so maybe there's something about the Richter scale. You can also do the same thing with hurricane, right? Hurricane have a ranking, right? You can see that a certain geographical area has a tropical cyclone, and you can say, oh, maybe there's a trend upward. I don't know if you know this, but global warming is here. It's not just real, it is here. So that if you go back successively, you take the highest temperature, whether on land or oceanic temperature, we have been hitting record year after year after year after year. Okay? When we say record year after year, we mean record that goes back from the beginning of civilization. Okay? We don't mean like going back to when the earth was just filled with volcanoes or something. No, not that. I'm talking about, you know, from the beginning of civilization. We've been hitting records. Same with forest fires and all kind of stuff. So You can do that. Okay, you can do that. Again, if you're talking about earthquake, then you're talking about rare event. So if you have a distribution among that, you're not going to get an extreme value distribution, right? But if you have something like ocean temperature, all right, then you can sort of test whether or not the extreme value in the last 50 years is worse than the previous 50 years. Okay, so I'm not sure how many of you are working with. Raise your hand beside one person. Raise your hand who's working with more like a global warming or kind of data. No. Okay, I kind of forgot what you were working on mostly. So okay, so that's okay. No, I don't have to remember. But do a good job. Okay, you can start with the presentation or not. I'm not really concerned with the presentation right now. You will turn that in at the event anyway. Okay. The only thing I would ask is, okay, let's do this. If I'm going to make an assumption that none of you is working on a graph data as a final project. So there's a balance between chapter 3, 4, 5, 6. Okay, maybe put chapter 7 as well. Okay, 3, 4, 5, 6, 7. 3, interactive visualization. 4, probabilistic modeling. 5, unsupervised machine learning. 6, supervised machine learning. 7, graph data. Okay, so among this, I want you to give like a weighting of how much your project is, right? Okay. So my project could be 90% supervised machine learning, 10% visualization. Visualization is going to appear at some point. So it's interactive visualization is probably not going to be less than 10 or 20% in all your project. Okay. And graph analytics or analytics on graph data, I would expect for a lot of you would probably be 0. Okay. But if you want to work on graph data and come see me extra time, I'm more than happy to give you as much time as you need. Graph data is the way of the future. I can tell you this. I can tell you this. Why? Okay, and this is the last point I'm going to make today. So far, I told you that we have 2 questions, right? Where are the data? And if you knew X, can you do Y? So far, I haven't done anything predictive about graph, right? Well, once words get embedded into a large language model, ChatGPT can predict the next word. That's how you get generative chat, right? Predict the next word. Graph, likewise, can be embedded as a vector. Once graph gets embedded as a vector, they can do graph prediction. For example, if graph represent volume of traffic in Bangkok, right? From one junction to the next, think of the red light as the vertex. Think of the street between red light as the arc. And think of volume between red light to red light as the volume of traffic as a weight. You can use this data to feed the neural network to learn about it. And they can maybe something like predict the volume of traffic on Raj Damri on Monday morning. Okay, so predictive is there, machine learning. So if I were to have a chapter 8, it would be something like supervised machine learning on graph, right? Except, we're not quite there yet. The technology is coming. Okay. And the last thing that you should know, and this is the most exciting thing right now, even more exciting to me than ChatGPT, protein folding. In biology, is one of the most difficult problems ever in history of man in terms of computation. Generative model can learn the graph structure, maybe of a molecular connection. And now they start to suggest things like protein folding. So AI is getting everything. Okay. Now the protein AlphaFold, which is the big news, the one that won the Nobel Prize, it's not necessarily based on graph structure. But I bet, this is my personal bet, the graph representation of molecular pathway in your body is going to be the next big thing. Now, I don't know if it is, but I'm betting on it. Okay. So we end with chapter 7, which is analytics on graph data. But you will notice that things like, is the graph connected? You know, there's built-in function, the centrality, there's a built-in function. There's no graph learning in here yet. Okay. So if this book were to have like another edition in 5 years, I would imagine, again, chapter A would be machine learning on graph data. Okay. But for now, your project, give me a weighting on chapter 3, 4, 5, 6, 7. Okay. And I expect chapter 7 would have a 0 weight. That's fine. I don't mind. Okay. But I really love graph data, guys. It's really a lot of fun. Okay. Okay. Sorry, I ran a little bit over time, but that's okay. I'll see you guys